Okay, as a review, I'm going to review just what we learned already because most are saying they stopped on refraction in light. Then others are saying the teacher who is not yet on call. Look at the rules determining acceleration due to gravity using a swinging pin to open to that page because these are vital rules that take us through the practical part of physics. And we are not sure whether we'll be having a practical paper or not, but there are some key areas that we need to put into consideration. So if there is anything I missed or any rule I've missed, Kale. So according to this one, we are going to use the graphical method. I'm just going to keep speaking. I hope we all did it about the one of acceleration due to gravity using a swinging pendulum. So what you need, a string at least 1 meter long, a pendulum bob, meter rule, retort stand, stop clock or stopwatch. Then slightly displace the pendulum bob to minimize errors in your results. So what to do? You set up the apparatus as shown, and then you slightly displace the pendulum from upward vertically and simultaneously start a stop clock or stopwatch. Then determine and record the time that pendulum takes to complete 20 oscillations. So these experiments must have varied in different schools and according to different teachers. Esther, I'm seeing complaints in that chat. I'm trying to cope up. At least time does not go when we have done a lot of nothing. So Esther, you're being very negative. I don't know why. So pardon me. I'm sorry. Apologies, Vanagi. Okay, so we plot. I'm not going to share because I did not prepare anything. Expected the teacher to be here, but just in the next few minutes, you'll be a part of us. So let's try to cooperate. We're discussing determining acceleration due to gravity using a swinging pendulum. I'm sure we all did this because most of us are saying we are what? In refraction in light, and then also doing waves. So we are doing a throwback, as you may say, in what? In um linear motion. So I requested that you just open back there, and then we know what, or we try to review on the rules that are needed, especially to be followed in the graphical method, because this is a practical part of physics. And you may never know that we will have a practical paper. Because personally, on a stream level, our teacher taught this. He was very careful because this is vital. First of all, that it's hard to discuss anyway, these numbers, but the rules that are considered in the graphical method, we have you noting down 1, 2, 2.5, and 5, the numbers that are above, and then the numbers that go below. And then that is for 1, it is 10 and 100, then below it 0.1 or 0.01. And then for 2, it's 20, then 200, and then 0.2, 0.02. Thank you, Esther. Submultiples and multiples. So I think she has summarized it. So you consider the vertical scale and then the horizontal scale. To get the vertical scale, you have the biggest number, the largest number minus the lowest number, divide by 10 of your values. So you divide it by 10 and you round it off to the next multiple or multipliers, whatever the case it is. Then for the horizontal, you divide by 8. So to get the values on that scale, for this to be efficient, I'm seeing people whose videos are on. You don't just listen, you're going to get lost. I guess you go back, just open back in your book and look at what I'm trying to say. Your graph book or something of the sort. Graph book, not even something I said, but your graph work that you did under this, because I'm sure we all did this. Anyone who did not, if you did not learn linear motion or you didn't reach where we are. Anyone, you said in the chat, okay, our teacher is here. Let me hand over to teacher Peter. I was honestly not ready for this. Teacher Peter? Before Teacher Peter comes in, sorry.
Yes, Ruth.
Okay. Before you come in, TechnoSpark Go over TechnoSpark Go 2020. Anyone who's using a phone or even a PC, please use your name. Techno Camon 15, Air Techno 15. The rest, you use your actual name for you to be able to participate. Okay, over to you, Teacher Peter. I'm sorry. I hadn't yet checked the participants.
Okay. Yeah. Okay, good afternoon to everyone who is here. I greet you all, and Ruth, thank you for keeping the class active as I was away. I'm sorry I've come in a bit late. I got some challenges with my network, but I'm happy I'm here now. And we are going to, now that we are going to S4, we are going to start on a new topic as the S4s, and that topic is going to be electricity. For my friends who are here, we don't have to see the teacher, but we have to focus on what is taking place on the screen, and we have to listen more. That is how you would be able to learn a thing or two. You're not going to see the teacher, but you'll hear the teacher talking about the things that will be displayed on the screen. So you're going to prepare, and we start on our electricity journey. I'm going to put the document on so that we can all be able to use it on the screen. Otherwise, as we start, you can tell me what you expect in electricity. What do you expect to learn as we study electricity? What are your expectations? Can I have some people telling me what do you expect to be learning as we look through the electricity?
Rona?
To learn the laws of electricity. Yes, one person is telling us he's going to be learning the laws of electricity. Any other person?
Okay, next. Kasumba Raziham. Rona, please mute.
I
Kasumba.
expect to learn electric circuit and how it works.
Electric circuits and how they work. Yes, any other person?
In the chat, Beatrice says she expects to learn electric charges.
Beatrice says he's going to learn electric charges.
And the Samsung, someone calling himself Samsung says the Excel says charges. Yes.
Okay.
And the types of current from travel. Yes. And then someone else says a flow of.
Okay. Okay, let us start our lesson now with knowing what we expect through in our electricity now. Yes, introduction to current electricity is the topic or the chapter that we are going to look at. Remember, we are all in the new curriculum, so this is the chapter that we are going to look for. And for this lesson specifically, we are going to have to look at EMF. We are going to know what EMF is, and we are going to learn more about cells, as we all know that cells are sources of EMF, and they are also sources of current or sources of electricity. So we are going to look at cells in details, knowing their types, their uses, and their limitations. There are four. We start with electromotive force. electromotive force is what we are calling the EMF. Please, if you are playing on the screen, you should stop it. It's not good. Then 10 to 25, then what? 25 to 35, 35 to 45, 45 to 50, 50 to 65, 65 to 80. Okay. If we are to start with the definition, we are defining electromotive force or EMF. Can someone be able to read, and you read for us what you see? How do we define electromotive force? Yes, Kasumba. Kasumba.
Okay. Electromotive force. This is the potential difference or work done in a moving column of charge across the terminals of a cell in an open circuit.
Okay, so you can mute. Kasumba has read for us that the electromotive force, which we also call the EMF, is the potential difference or is the work done in moving a column of charge across the terminals of a cell in an open circuit. Now, if someone says a column is a unit of charge. Charge is how we measure our electricity. The quantity of charge is how we can measure electricity. That's why you say I'm going to charge my phone. The charge on my phone is low. All that is because current stored is called charge. So the unit for charge is coulomb. So if we move a coulomb, that means one coulomb of charge across terminals of a cell, for example, from a positive terminal to a negative terminal, then what happens, or what you have done there, is said to be the potential difference, or the work that you do in moving a coulomb from a positive terminal to a negative terminal, is what we call a cell, is what we call EMF of a cell. The reason why we call it potential difference is because the terminals of a cell, remember a cell, for example, a dry cell has a positive terminal and a negative terminal. So the terminals of that cell, one is on a positive potential, whereas the other is on a negative potential. The positive side of a cell is on its positive potential, and the negative side is negative potential. So the difference between the positive potential and the negative potential is what we call the potential difference. So if we get a coulomb of charge, or a positive charge, from one terminal to another, the work done in doing so is what we call EMF. And if they say in an open circuit, they mean in a circuit where there is no load connected. A load, for example, a bulb For example, a resistor, anything that can drain our cell. If there is nothing connected in the cell, or if there is nothing connected in the circuit except for a cell and an instrument that measures potential difference, then what we have got is what we call the EMF. Is what we call the EMF. And from our text there, we see that it is also the maximum voltage that a cell can provide. So a cell can provide the maximum voltage. That maximum voltage it can provide is called an EMF. But they are telling us that because cells have internal resistance within a cell, since there is internal resistance in the cell, then the useful potential difference is less than the EMF. The useful potential difference is less than EMF sometimes because of the internal resistance within a cell. And they are telling us that one of the major sources of the EMF are cells. So I'm going to ask you to tell me anything that you think I should repeat for you in the definition and on the notes that I've just said about EMF. You can write in the chat, then Ruth will read what is in the chat, then I will answer before I change to another slide. What do you think we should say again? I should go through again. So someone saying terminals. Someone is telling us what causes potential difference. Please clarify. Other sources of the EMF, we will see that. So, potential difference. Okay. So we are going to go through now we are going to get a clear aspect on the electric potential and then potential difference. So from this document that we have here, they are telling us that if someone says I have potential, it means that someone has the ability to perform a specific task or to do some work. If I say, so you have potential to pass, it means that I'm sure you have the ability for you to pass. So potential, in terms of what we are on now, is the work done to move a charge from one point to another. And those points will be on different potentials. If I move a charge from one point to another, By the way, moving charge from one point to another is only possible if the 2 points are having different potentials. They have different abilities to do some things. So if the 2 have different abilities or different potentials, then I can move a charge from one potential to another. And because moving a charge, I have to do some work, then that work done is what we call the electric potential. Work done in moving a charge or a column of charge from one point to another. There is a figure that we are going to look at, and they're telling us in that figure that we are going to see. Let's first put the figure here. Now, if you look at this figure, we have positive potential and we also have negative potential. If we look at that figure there, we have a zero potential. Points that are at zero potential are points on the Earth. It is believed that the Earth has zero potential. So below the Earth, there are points that there are things or there are points that have negative potential. Negative potential means there is a lot of negative charges at that point compared to others. And if they say positive potential, it means that there are more positive charges at that point. So if I'm to move a positive charge, remember, charge flows always from negative to positive. But if you have to get a charge from the positive to bring it to a negative side, then that is where the doing work comes from, because you have to overcome a certain force and you have to move a distance. Then that's where we say that work done, because there is a force that we have to overcome and there is also a distance that we have to cover. So they are telling
Mr.
us,
Nzubuga,
yes.
sorry for interruption. Who Alinda Joan is complaining that you are fast, and then
Sure.
someone who's using Samsung is asking why does the Earth have a potential of zero?
Okay, we are going to
A zero potential, sorry.
we are going to look at that. Why Earth has
And
potential.
then Mr. Paul Luhurwa brings a suggestion in. I think before we come to electromotive force, is it? Yes. We can start from electricity as a form of energy, what we covered in senior 2 work. And let me first finish reading. Let's see. Okay. I think that is it. And then Esther is also complaining, teacher, you're too fast. I also do complain. Oh, it's because of my network.
I think it's
Especially
network.
electromotive force.
I think
I
it's
really
network
didn't
issue,
think.
but we are going to I'm going to try to go a little bit slow to see that each one of us at least picks that, because the topic that we are looking at now, we must know that first of all, we must know that electricity, first of all, is a form of energy. That is it. How electricity comes up, how electricity comes up, how we get electricity is what we are looking at, because we are going to be looking at, first of all, electricity from cells. And we are going to be looking at how does electricity come from those cells. Then we will go to current electricity. We see how it is generated from the dams, how it is transferred from one point to another, and how it reaches our appliances. So to know all that, we have to start with knowing about potential and then electromotive force. And we'll be going on adding one thing after the other. Why I started with electromotive force is because the topic, if you look at it in our curriculum, if they say introduction to electricity, they are sure that you know it's a form of energy, and they are sure that in the things that we are going to be looking at, we are going to be seeing sources of electricity and how they work. So knowing that it's a form of energy, I know each one of us here, by the time you get to S4, you know that. That's why I used the book for the new curriculum, Introduction to Electricity. They start with EMF. That's why I also chose to start from there. So there is no way I could go back to senior 2 work, then I come to that. I'm sorry for starting where I had to start from for my friends in senior 4. Then about being speedy, for that one, I'm going to try and we go slow to see that each one of us has picked something from what we are studying.
Mr. Nsuga, I have
Yes.
I have a question. Let's first take back to that previous screen on potential. That, of course, I say I'm sorry, we have not yet reached there. But potential, you said, okay, according to this file, potential is equal to work done out of charge moved. And
So we are
then
going
the
to see that. Don't
symbols.
worry. Mm,
Oh, okay, please.
okay. Okay, first of all, we started from the other document, and they were defining for us electromotive force. And they told us electromotive force is either potential difference or work done in moving a charge from one terminal to another. Those are terminals of a cell in an open circuit. And after knowing that it's the potential difference, a person asked, then what is potential difference? Then I told you that potential difference, I told you that potential difference is the difference between the abilities of work done at specific points. I've told you that there are points that are at a positive potential because there are positive charges around that point, many of them, and there are points at a negative potential because those points have negative charges around them. So since there are points from positive, there are points at the positive potential, and there are points at the negative potential because of the reason that I've told you. The 2 points, one at a positive, the other at a negative, we say they have different potentials, and therefore between them there must be what we call a potential difference. A potential difference comes in because one is at a positive potential, then the other is at a negative potential. So have we got that about potentials? Because one has more positive charges, then another point has more negative charges, then between them, because one is at a higher potential and the other is at a lower potential, then the two, between them, there must be a potential difference, a difference in potentials. That is what it means. Let us read here. There is something that I want us to read here, and then we continue. There is somewhere they are telling us about positive and negative potential. They are telling us that in the figure that I'm going to put on, work must be done to move positive charge from Earth to a conductor A. We are going to see where conductor A is. And conductor A is at a higher potential than the Earth, and its potential is taken to be positive. Then on the other hand, we are having that work must be done to move a positive charge from B to Earth. B is at a lower potential, and therefore its potential is negative. So what I have told you to make things for you easy, if you look at if we look at this diagram here, you see there is a point on a positive potential and there is a point on a negative potential. One is A, that is the positive potential point, and B is the negative potential point. So the difference between their potentials, positive 10 and negative 10V, according to the diagram, I'm using the diagram values, the difference between those two potentials is what later we will call potential difference. So in this, they are telling us that if two conductors or 2 points are at different potentials, then there is a potential difference between them. And electrons or charges will flow always from where we have a lower potential to where we have a higher potential, or towards a more positive potential thing. So if they say potential difference, they mean the work done in moving a column of charge from one point to another. Potential difference is the work done in moving a column of charge from one point to another. And I've told you that moving from one point to another means that those 2 points are at different potentials. So it's only possible to move from one point to another if the two are at different potentials. And they have told us that electrons will flow, or charges will always flow from lower potential to higher potentials. And the difference between points potentials at different points is what we call potential difference. So that is where we started from the definition of electromotive force.
Mr. Nsubuga,
Yes.
what is now the difference between potential potential? Because
What is the
the
difference
definitions are not the
between
same.
the
Electric
definition?
potential and potential difference, because electric potential, you said, is the work done to move charge from, I don't know if I'm done, from one point to another. And then potential
Sure.
difference, it means I
Now,
have a
potential
wrong
difference.
definition. Mm,
Now, potential is on a point.
mm,
Potential is on a point. What a point can do. Okay?
yes.
Yes, maybe a point is positively charged, so we say it's having a positive potential. Or when it's negatively
So
charged, we
this
say it's
defin
having a
mm,
negative potential. So the
mm,
definition that we have is for potential difference between 2 points. Okay?
mm.
So it's the definition that we have.
I still don't get it. I don't know why. I think I have a wrong definition. Wrong definition on potential difference. Let me now first define potential difference. I've written down that it's the work done in moving a column of charge from one
Yes,
point to
to
another.
another. Then that is
Is
potential
that
difference. What you have
correct?
is a definition for
Is
potential
that
difference.
correct for potential difference?
Yes.
Mm.
And that is what I want you to know for now. Potential difference, that it's a work done in moving a column of charge from one point to another. And if that potential difference is across terminals of a cell, if you have a dry cell, you can check it has a positive terminal and a negative terminal. So if that potential difference is across the terminals of a cell, then we change its name from being only a potential difference to being an electromotive force. The potential difference, or the work done in moving a column of charge. Remember, potential difference, they said from one point to another, but here in EMF, we say across the terminals of a cell. Across
Mr.
the
Nsubuga,
terminals of a cell. Yes?
I'm asking, what is electric potential in this case now?
What is?
Electric potential.
Then I have to go back to, I will define it well. I think, let me first go back to the other document so that we can all see it. Okay, now what we first defined was potential difference between 2 points. But then we need to know what a potential also is. So I want someone to read for us from what we have on the screen. what we have on the screen, the definition that we have on the screen. Can someone read it for us? Now we are defining what electric potential is. Can someone read it for us?
Okay, let me read.
Mm.
I'm reading from electric potential. The definition, right?
The earth. Let's start
Okay.
from the earth.
Okay, the earth potential is taken to be zero. The potential of any given point is equal to the work done to move a small positive charge from Earth up to that point. Then
You read
the
again?
potential is equal to work done. Okay, the
You
Earth
first read
potential
again.
is taken to be zero. The Earth potential is taken to be zero. The potential of any given point is given to the work, is equal to the work done to move a small positive charge from Earth up to that point.
Okay, so we have two definitions now. One is for potential, and the other is for potential difference. If you are defining potential, then the charge has to be coming from Earth to that point. Then if you are defining potential difference, then it has to be coming from one point to another. Have you realized the difference between the two? If you are defining electric potential, we say from Earth to a point. When we are defining potential difference, we say from one point to another. I think now we have got the difference between the two.
Thank you so much. So you just, what I do, I just interchange the very definition of potential difference and then have it, okay, it is the work done in moving a column of charge from one point to another. So I have, it is the work done in moving a column of charge from the earth.
From
Is it?
Earth, yes, to a point.
Okay, thank you so much.
Okay.
Mr. Sansuga, before you move on, someone is asking in the chat, I didn't get her name. Is it Priscilla? Someone is asking, Infinix
What
is
is a column?
asking what? Yes.
Yeah, a column, I said a column is a unit of charge. Like any other SI unit, if someone says one column of charge, then they are saying, they are giving us charge, the unit of charge. So charge is measured in columns. I think Priscilla is the one that had asked that. Okay. Okay. I think we are all now sure about what potential difference is. And since we know what potential difference is, we also know what electromotive force is. Because the electromotive force, what changes is that instead of us saying from one point, work done in moving a column of charge from one point to another, we say it is the work done in moving a column of charge across the terminals of a cell in an open circuit. And I said, if someone says an open circuit, it means that he's meaning a circuit where the cell is only connected to the instrument that is going to measure potential difference. There is nothing else connected in that circuit. Then I've seen someone in the chat saying, you have something you want to ask. If you have something you want to ask or something that you want to say, the reason why we mute all of you is because so that you can be able to listen to one person at a time. So if you really want to ask something, or if you want to say something, you either write it in the chat or you raise up your hand. I will click here and you will be able to unmute yourself and then you ask your question. Someone is asking for the definition of EMF. I've said EMF is the work done in moving a column of charge across terminals of a cell in an open circuit. Then I've said that if someone says terminals of a cell has a positive terminal and it also has a negative terminal. And if someone says open circuit, it means a circuit where the cell is only connected to an instrument that is going to measure potential difference. Now, I don't want to go on jumping from one thing to another, If I tell you that for now, take a column as a unit of charge, then I really want it to be at that, because I know there is a definition for column, but when I bring it now, it brings other questions and we will find ourselves not progressing in anything. Just pay attention to the simple things, and then as time goes on, we'll go on learning and one thing after the other. So we don't have to go on jumping from one thing to another. We will not learn. I told you cells are one of the major sources of EMF, electromotive force. Now, because EMF is across terminals of a cell, it makes a cell a sole source for EMF. Maybe others will come in, maybe generators, maybe other things that produce EMF, but a cell is what gives EMF, because it is across terminals of that cell that we will get the EMF. Others will give you a potential difference. Others will give you voltages, but they won't give you what we call EMF. The name will change, though the units might be the same and the meaning might be the same, but a cell will get EMF from there. Hope you get it. So people were asking for other sources of EMF, not for now. We are going to be looking at cells, because if someone talks about EMF, then a cell is the first thing that has to come in our mind. So I want us to progress and look at electric cells. Someone was asking, I think some time back, someone is asking me what internal resistance is. Now we will learn resistance as a whole later in this topic, but since I've talked about internal resistance, we define internal resistance as opposition to flow of current within the cell itself. Opposition to flow of current within a cell itself. So electric cells are devices that can produce electricity, and they are telling us by chemical action. So anything that can produce electricity by chemical action is what we call a cell. So you can ask yourself which things can produce electricity by chemical action. So if anything can produce electricity by chemical action, then it qualifies to be called an electric cell. And it's also a device that converts chemical energy to electrical energy. So if someone asks for which energy is stored in a cell, it is chemical energy. And when that cell is connected to something, then it converts the chemical energy to electrical energy. That electrical energy is then converted to other to other forms of energy. And cells are divided into two classes or two types. We have the primary cells, and we also have secondary cells. Primary cells and secondary cells. Now, a person is asking me what is the difference between a battery and a cell. Now, for something to be called a battery, we must have many cells put together. If they say a battery, it means there are many cells that have been put together. So if we say a dry cell, that means it's one. But if we join them, then they call them a battery. Though for us, we call everything that is called a cell, we also call it a battery, but that is the difference between the two. If you find a friend asking something that we have already said, maybe a definition or something, and you still remember it, you please help me put it in the chat such that we don't go back to certain things. Things like internal resistance, I'm sure Hannah has the answer. So Hannah, you put the answer in the chat. So the difference, I think I've given you a little difference between between a battery and a cell. A battery, we believe it's a collection of cells. If we add cells together, we come up with a battery. So we have two types. We have primary cells and secondary cells. But what is a primary cell and what is a secondary cell is now what we are going to look at. So can I have someone reading for us definitions of a primary cell?
Priscilla? Priscilla, unmute. Okay. Priscilla, we cannot hear you. Okay, Saida.
A primary cell is a cell that produces current as a result of an irreversible chemical reaction.
You have not finished our definition, Saida.
Oh, okay, let me repeat. A primary cell is a cell that produces current as a result of an irreversible chemical reaction, i.e., cannot be recharged when it runs down.
Okay. So if someone says a primary cell, then it is that cell which produces current as a result of irreversible chemical reaction. It means that if the reaction has taken place, it can't be reversed back. You can't take back the reaction. So since we can't take back the reaction, it means that once the charge runs down, you can't recharge that cell. Cells that fall in that category, when you know that you can't charge that thing or you can't charge that cell, then that one will be called a primary cell. Whereas for a secondary cell, a cell produces electricity as a result, or produces current, as a result of a reversible chemical reaction. The reaction is reversible. You can change the reaction. Maybe if it started from somewhere and it ended somewhere, then you can start from the end and you come back and you get what you had at the beginning. So the reaction can be reversed. In other words, these ones can be recharged when they run down by passing current back through the what? The cell. So what happens is that the batteries the cells that we can charge are those ones whose reactions, the chemical reactions inside those cells can be reversed. Whereas those ones that we cannot charge, their reactions cannot be reversed, or they are irreversible. And they are giving us examples of each. Examples of primary cells. We have simple cells. We are going to start asking ourselves now, what is a simple cell? We are going to see that. Then dry cells. Then we have a wet cell. It was named after the person who made it. So you can read that name. I don't think I'll be perfect reading it, but you can find means of reading that name. So we have a simple cell, we have a dry cell, and a Lagrange wet cell. So those three are examples of primary cells. Whereas secondary cells, we have a lead acid accumulator and we have alkaline cells. Now, lead acid accumulators are like the car batteries, and the alkaline cells, those nickel ion, are like the ones that we have in our phones. So all those ones are secondary cells. So now a person is going to start asking, what are the dry cells and what are the wet cells? What do I need to know about a simple cell? So that is what we are going to start doing. We are going to start with a simple cell and we find out what a simple cell is. Then we find out what a dry cell is. And then we find out what a wet cell is until all primary cells are done. So let's start with a simple cell.
I tell P17 your hand is up. Please unmute if you have any question or you just forgot it up. Okay.
Okay, so let us start with a simple cell, how it is made, and what do we need to know about it. Can someone read for us what we have in a simple cell?
Eva?
Yes, you read for us. Anyone who is reading?
A simple cell is made up of electrodes, that is a copper rod, which is a positive electrode, and a zinc rod, which is a negative electrode, that are dipped into an electrolyte, that is dilute sulfuric acid, and are ignited by a piece of conducting wire. The more reactive metal in the reactivity series, that is zinc, forms the cathode, while copper forms the anode. The electrolyte being dilute sulfuric acid ionizes as below. So sulfuric acid ionizes to give us hydrogen ions and sulfate ions. So how a simple cell works? The zinc plate slowly dissolves and goes into the solution as zinc ions, which displace hydrogen ions to form zinc sulfate. In that reaction, zinc dissolves, forming zinc ions, and the reaction became military equation. The displaced hydrogen ions move to the copper plate. The electrons from the zinc travel through the external circuit and arrive at the copper electrode where they combine with the hydrogen ions to form hydrogen gas. This flow of electrons from the cathode to anode causes the flow of electricity from the anode to the cathode. Hence, the voltmeter deflects.
Favor, your hand was up.
Are you hearing me?
Yes,
Have you been hearing me?
I'm hearing you.
Sorry again.
Oh, we are hearing you. If we are hearing you well. So they are telling us that a simple cell is made of electrodes, a copper rod, and a zinc rod, and they are dipped into an electrolyte, for example, dilute sulfuric acid, and they are connected by a piece of conducting wire. So you first note that, and we are going to know what does sulfuric do, why the zinc, why the copper.
The sense of guys still on?
I'm still on.
Oh.
Electrolytes ez'enjawulo mucungwa niki.
So what we have to note about a simple cell is that if any one of us can also do it. The reason why we call it a simple cell is because once you have electrodes and an acid, which is dilute or which is not too strong, then this reaction can happen and it can produce electrons. For example, they are telling us if you have a copper rod and a zinc rod, why copper, why zinc? They are going to, they told us something below here, but they're telling us if I have a copper rod and a zinc rod, and then I dip them into an electrolyte such as dilute sulfuric acid. Now in labs, in our labs at schools, when we are doing such experiments or when we are looking at a simple cell, instead of using sulfuric acid, some people may choose to show that fruits too can give electricity. For example, if we have an orange inside it has citric acid, and it can also give a small current. So a simple cell can also be got from fruits, but it can also be made, as they're telling us in our notes, that we get electrodes and we dip them in an electrolyte, and then we connect a piece of wire. A piece of wire must be connected between the two, because one is our positive and the other is our negative electrode. How do I say this is positive, this is negative? They have given us a reason here. The metal which is more reactive in the reactivity series forms the cathode. Cathode is a negative terminal or a negative electrode. And the one which is less reactive makes the anode, which is the positive electrode. So someone has asked me, does any acid work? So long as reactions can take place, like the one of sulfuric acid, then it can work. The reactions, we are going to see them below there. So they are telling us those ones which are more reactive in the reactivity series will form the negative terminal or the negative electrode, whereas those ones which are less reactive in the reactivity series. So you have to visit your chemistry and you check reactivity series of metals. Which one is more reactive? Which one is not? Which one is more reactive? Which one is not? And then you will know which one will form the anode, which one will form the cathode. Now, sometimes in our questions that they set for us, they will not tell you which one is positive, which one is negative, but they will give you the names of those metals. So it is you as a person who has to know that zinc is more reactive than copper, or this type of metal is more reactive than the other. So the one which is more reactive makes the negative electrode, whereas the one which is less reactive makes a positive electrode. That one you should not eat. And the electrolyte that we use must be able to ionize. Ionize means it must be able to separate positive ions from negative ions once things start to work. So they are telling us that the electrolyte, being dilute sulfuric acid, ionizes as below. So the ions that are given off from sulfuric acid, we have hydrogen ions, and we also have the ions of the sulfate. So you see those two ions that are given off in this
Mr. Silva,
reaction. Yes?
sorry for interruption. Oh, Chirabo Paul in the chat asked earlier on, is there a specific material the conducting wire is supposed to be made of?
So long as it conducts, so long as the wire is a conductor, it doesn't matter.
And then she's asking, is there a reason why the more reactive metal forms the negative electrode?
Yes, and we are going to see it in the reactions below.
Oh, so teacher, I also had the same question. I was wondering, but I remembered you said electric potential is from the earth to a point. For some reason, I don't know if I was confused because I expected, since you said that the positive has a higher potential, and then let me see. The positive forms a higher potential at difference than the negative side with the illustration of what? Of the earth. So I think I'm the confused one. Let's go on. I'll catch.
Okay.
And then Galaxy is asking, sir, please summarize how a simple cell works.
Yes, we are going to summarize that. I was still telling you about what is made, a simple cell is made of. It's made of electrodes, and these electrodes must be metal electrodes, and one must be more reactive than the other. And then we must have an electrolyte that is able to ionize. And this is a simple diagram that I have for this one. Here is the simple diagram that I have for a simple cell. This one here. So to have that diagram with how this simple cell works, because zinc is reactive, because zinc is more reactive than copper, it will react fast. Reacting means that it will react with this it will react with the sulfate ion. Remember, our acid ionized into hydrogen ions and sulfate ions. Why is it able to ionize? Because it is in its dilute form, and since it's aqueous, then it has both positive and negative ions. After that, because zinc will be more reactive, or it reacts faster, then before it reacts, it will also change from being a metal to being aqueous, because now we have dipped it into the zinc. So what happens? We will get 2 electrons being lost. 2 electrons being lost from zinc, and then it will become they will become zinc ions, which are aqueous. And those zinc ions, which are aqueous means they have some water in them, or they are able now to react with the others for the sulfate ions, not as solids, but now as in the aqueous form. So the zinc and the sulfate ions now will come together to form zinc sulfate. Now, if you look at what we have in our diagram, you are seeing that the zinc we have the zinc plate, and they are telling us that this zinc plate ionizes also to form iron, the zinc 2 ions, which are aqueous, and then the electrons that are given off. So they are telling us that the displaced hydrogen ions move to the copper plate. If you want to take notes and you have a phone, you screenshot. If you want to take notes here, but I'm going to send the whole thing in our group such that we all have them. So you don't have to worry. What you have to do is to listen and try to understand, such that when you are reading through those notes, you'll be knowing what we really talked about. So I was still telling you that the zinc and the sulfate ions will come together. And remember, we had hydrogen ions from our electrolyte, that those hydrogen ions will move to the copper plate. Then the electrons that this zinc gave off, these electrons here, where is my... These electrons here that the zinc gave off, they are telling you that those electrons move the electrons from the zinc, travel through the external circuit. Now, someone might ask what the external circuit is. The external circuit is the wire that we used to connect the 2 electrodes, the positive and the negative. So the electrons, for them, they will flow through the external circuit and arrive at the copper electrode. And when they arrive there, they collide with the hydrogen atoms that went there, and they will form water. They will form what we call water there. So the electrons, not water, they will form hydrogen gas. Sorry about that. So the hydrogen ions and the electrons that have been flowing from zinc to copper will combine there and form hydrogen gas. So how we will see that hydrogen gas is formed, we will see bubbles on the copper plate. We'll see bubbles on the copper plate. And when we see those bubbles, we know that hydrogen gas has been formed at that point. But as the electrons flow from the cathode to the anode, it will cause current to flow in the other direction. I think you can be able to see that there, that when electrons were flowing from zinc to copper, current was flowing from copper to zinc. Current is the flow of charge. Charge can either be positive or negative. So when charge flows, for example, when the electrons are flowing, then also current will be flowing. And if we had connected something, maybe an ammeter or a voltmeter, the reason why we say that current has been flowing is that we will see that voltmeter deflecting, or we'll see a change in how that voltmeter is reading because of the flow of current. So in summary, what we have there, if you look at that heading, how a simple cell works, what you see there is briefly how that simple cell will work. First of all, the zinc dissolves and goes into solution as zinc ions. The zinc ions will displace hydrogen ions, and when the hydrogen ions are displaced, the zinc ions and the sulfate ions will join together to form zinc sulfate. Then the hydrogen that were displaced will move to the copper, and since they have moved to the copper, the electrons from the zinc will also move, but through the external circuit, through the connecting wire, and then they will meet there to form hydrogen gas at the anode. And the flow of electrons will be seen when the voltmeter deflects. And when the voltmeter deflects, we say that there has been flow of current. Now, someone was asking me if electrons flow from a negative to positive, then why does current flow from positive to negative? I think now that one is going to be an answer that we are going to see when we start looking at electric current. We are going to see why does it flow from positive to negative. Atenga electrons flow the other way around. So that is what we are going to see. Someone is telling me to add them in the group. If you have a group link, please put it in the chat so that people can be able to join themselves there. So I think all of us now can explain or can tell or can try out an experiment that shows that shows what? That shows that how a simple cell work. We can get an orange if you have a zinc plate or a copper plate, or if you have any two metals whose reactivity series you know, and you know that one is more reactive than the other, and they can react with an acid. You can try this experiment at home, and you see if something is given off. Now at home, we may not have a voltmeter, but you can get a LED bulb. A LED bulb is a small bulb, which will use a small current. We normally use them in electronic circuits. For example, if you have ever opened a circuit board for a radio, there is some small red bulb that is there. That one is what we call a LED bulb. Someone is asking me, can't we use lemon? Lemon and orange are almost the same. No, the one in torches is not a LED bulb, and you'll be disappointed if you use it, because for it needs a little more current. That one is not a LED bulb. LED is a very small bulb, but you can easily access it anywhere. If you can send a parent in town, they can sell it to the parent at 100 shillings or less. a LED bulb. So a simple cell has defects, has problems also. And they have told us that it works for a short time, after which the current stops to flow because of two problems. One is called polarization, then the other is called local action. So we are going to talk about those two defects, and I think that is where our lesson will stop according to the time that we have. We are going to look at the defects of a simple cell, the polarization, and the local action. So we start with the polarization. The definition for polarization is the collection of hydrogen bubbles at the anode which partially insulates it from the electrolyte. If they say partially insulates it from the electrolyte, insulating means something like you separating it from the electrolyte. Otherwise, the electrolyte can no longer access the anode. It can no longer access the anode. So we remember when we are looking at the action of a cell, you remember we said that these hydrogen ions that are displaced by the zinc ions are moving towards the copper electrode. And this copper electrode, because of the electrons that flow from zinc to copper through the external circuit or through the connecting wire, and these hydrogen ions that are coming towards it, they form an hydrogen gas, and then bubbles will be developing around the electrode. Now, when these hydrogen bubbles become too many, they separate the electrode from the electrolyte. They separate the copper from the acid, such that the hydrogen now that comes in can no longer reach the electrode. And if that happens, it means now current can no longer be got. And that is what we called polarization. So we defined it as the collection of hydrogen bubbles at the anode, which partially insulates it from the electrolyte, and this slows down and eventually stops the working of the cell. Now I'm seeing people sharing their phone numbers in the chat. That is too risky. Please don't do it again. It is better you join using a link that has been given to you. Sharing phone numbers in the group is so risky. Please don't do it. So that is polarization. And how can we prevent it? Preventing it is by occasionally brushing the anode. Brushing means that anytime you see the bubbles coming up, you try to remove them with something that is safe, and by that you will prolong how your cell is working. Or you can use something that can depolarize. Depolarizing means something that can make that hydrogen become water now, like potassium dichromate. So that is what they are telling us. So you occasionally brush, or you add a polarizer. Definition for polarization is still on screen. Collection of hydrogen bubbles at the anode, which partially insulates it from the electrolyte. That is it. Then lastly is the local action. Now, as the zinc electrode, remember they told us that the zinc electrode will dissolve. When the zinc electrode dissolves, as a result of the impurities it has, then you'll find out that it will keep on reacting with the acid to form hydrogen bubbles also. And once the hydrogen bubbles accumulate, then we know what happens is we can no longer get the electricity as we have been getting it. So the gradual wearing down of the zinc electrode as a result of impurities is what we call local action. And how we can stop this is either using pure zinc, something which has no impurities in it, or cleaning it with concentrated sulfuric acid and then rubbing it with mercury to form the mercury zinc amalgam to make it something that is stronger for it to wear down like it does if it's just alone. So you can either use pure zinc, or you can do that what they're telling us in the chart. Polarization and local action are one of the problems that we get with a simple cell. So I'm going to put a question here for you to answer in your free time, but it's going to be regarding on what we have seen, regarding to what we have seen from EMF to what we have now, a simple cell, such that in our next lesson that we get, we will talk about a dry cell, wet cell, and then the secondary cells. And after cells, we'll go in for real current electricity, like we have to do. So the question, I'm going to type it here, and this is how it goes. I want to text. Come, my Zoom cannot type. Yes, Okay. Okay. Any question as I finish typing this question here? Okay. Ruth, some people want to be unmuted. I don't know why, but if someone's hand is up, you can unmute them and they are able
Okay.
to speak what they want.
Please unmute. I've asked you to unmute. Huawei, Mega, something like that. What's your name?
Excuse me, sir.
You are excused.
Yeah, as we are saying, we can also carry it out at home. Yeah, so can we use other metals other than copper and zinc?
Yeah, so long as you can, you go and visit the reactivity service, you check the
All right.
reactivity, so long as those metals have the qualities that we have said, one must be more reactive than the other.
All right. Okay.
Okay, thickness back 4. Thickness back 4, please unmute. Okay, cider.
Excuse me, Master Nsubuga. You
Yes.
talked about a voltimeter. What is a voltimeter?
A voltimeter is an instrument that we have in our labs used to measure potential difference or voltage or EMF.
Okay, thank you so much.
Okay.
Excuse me, sir. If you want the
Yes, you are excused. If you want to do what?
current to be like increased, what can you do? Like, is it a must that, like, for example, if you want to make an experiment of your own, can you use 2 oranges? Will it really come out?
2 oranges, you must be able you must be to connect those oranges, because we haven't learned about connecting cells in series or parallel, because we have those connections that can help you add on a cell on the other. But maybe instead of using the orange itself, you can get the orange juice and then you use it in a container. That one can also work. Any other question?
Imran. Imran, unmute. Okay.
What I was asking was like,
Imran, you keep muting yourself. Abed. Imran, please send your question in the chat.
Yes, sir.
Yes.
Hello. And the
Yes.
polarization method also work in magnetism.
Nope. It will not work. Polarization
Okay, sir.
that we look at here is something else.
Okay,
Any
thank
other
you.
question? If you had a question and you sent it through the chat, please air it out. Because there were very many questions that came in.
Ruth and others have put the question in the chat. You look at it and you help me try it out, and you'll be sending your answers, or we'll be discussing some of the answers as we start our lesson where we'll meet next.
Even a lemon
So let us look at that question, copy it down, and that is what we are going to be using to do today. So are we done copying the question? If you are done copying the question, then I think our lesson will end here. We will meet again in our next lesson. I'm sorry for the inconveniences, the coming late, and the speed that we started with. I think in our next lesson, everything will get better. And I believe that we will understand even better when we have some videos to watch about these things that we are learning. Otherwise, I wish you a very, very wonderful evening and a nice holiday and a happy new year. The question is in the chat. Let me send it again for those ones who have not yet copied it.
Okay, as we finish up, anyone to lead us in a closing prayer? Anyone? Cynthia? Cynthia, please lead us in. Okay.
So let us pray. Most Holy Father, we thank you so much for this lesson. Thank you so much for everyone that has attended. Thank you so much for the teachers. And we pray that in the next lessons you help us to understand well through Jesus Christ. I do pray and believe.
Okay, thank you all for attending. Same time at 2 tomorrow.